Hello everyone, welcome to my video. So in this particular video, I will explain the concept called as pulse amplitude modulation. In analog modulation, we have studied already, we know that what is amplitude modulation is. Amplitude modulation is a process where we actually change the amplitude of the carrier signal, high frequency carrier signal, proportional to the amplitude of the message signal. Now in this case, in the pulse amplitude modulation, we are going to change the amplitude of the pulses proportional to the amplitude of the message signal. Now, what are the different types of PAM? In a short, we call this as PAM, pulse amplitude modulation. So different types of PAM. Under that, we are going to study one method in this particular video. Now, coming to the the introduction part over here. So as I told earlier, we are going to consider a regularly spaced sampling signals, the set of pulses, okay, and we are going to change the amplitude of those set of pulses proportional to the amplitude of the message signal. Okay, we can take instantaneous signals or delta functions as sampling signal. We call this as ideal method, or else we can take the rectangular shaped pulses where we actually change the amplitude of those rectangular pulses proportional to the amplitude of the message signal. That means whenever the amplitude of the message signal varies proportionately, we are going to change the amplitude of the sampling signal also, a discrete time sampling signal. As according to sampling theorem, as you are aware that we have to take how many samples? We have to take Fs number of samples. That is, in case, suppose say, I am going to take a Fs number of samples. The sampling theorem says the number of samples what we take of the analog signal which you want to convert into digital, okay, should be always more than or at the most minimum, you can say, twice the highest frequency in the message spectrum. That is, Fs should be more than or equal to 2 times W. That means if my W, the highest frequency in the message spectrum, let me say the speech band. Okay, if I take a voice band or a speech band, the highest frequency is taken as 3.4 kilohertz. That is 300 to 3000 hertz is the range of frequency we consider for speech band, and practically we go with a 3.4 kilohertz. Okay, now if I choose Fs, the minimum sampling frequency, as say twice the W, because my minimum sampling frequency should be 2 times W. Okay, and we call this as the Nyquist rate. The minimum sampling frequency is actually called as Nyquist rate. It should be equal to how much for this example? It is equal to 6.8 kilohertz. It is 6.8 kilohertz. But practically, we actually take sampling frequency more than that due to certain reasons, which I mean, that. So it is Fs equal to 6.8 kilohertz is the minimum sampling frequency, but practically the standard frequency selected in case of say pulse code modulation, it is 8 kilohertz for a voice band. That is 8,000 samples we have to take per second so that you can convert the analog signal into the digital form, and so that you can reconstruct the signal in the receiver and you get back the original analog signal. Okay, so this is the standard frequency they use, or in general, the sampling theorem says the sampling frequency should be more than or equal to 2 times the highest frequency in the message spectrum. Right? Now, 1 second. Yeah. So, we can have two different types of PAMs, pulse amplitude modulation, the practical methods. The one is called as natural sampling, okay, where the message signal amplitude actually follows, or the sampling signal, whatever we are considering, the amplitude of those sampled signal will actually follow the natural variation in the message signal. That means if I show it in the waveform over here, just look at this. So this is my analog signal which I want to take the samples of this particular analog signal. Okay, the second one is the set of sampling signals which are actually repeating for every ts seconds. Let's look at this. It is repeating for every ts seconds here, right? So the first rectangular pulse is taken over here. The second one, that is time delay, is around ts seconds. What is ts? Ts is the sampling time. So that means I'm going to take a sample of this particular analog signal at every ts seconds. Okay, so when I take the samples of this analog signal, I'll get a rectangular pulses but with a varying amplitude, where the amplitude variation is actually proportional to the given message signal. Just look at this. If I touch the envelope, if I touch the peak of all these pulses, it is same as this particular signal. Right? Now, in this case, just look at the waveform. This shape of the pulse or top of the pulse is actually following the natural variation or whatever the amplitude variation we have in the analog signal or the first signal, the message signal, right? That's why this method is actually called as natural sampling. That means natural variation is actually happening in the amplitude of the sampled signal, which is proportional to the amplitude of the given message signal. So this is the first method actually, the natural sampling. Now the second one is something called as a flat top sampled signal, okay, which we are going to study in this particular video. Okay, so the top of the each rectangular pulse is actually maintained flat in this case. Just look at this representation compared to the previous one where the amplitude of the message signal was following the natural variation of the amplitude of the given message signal, correct? Now in this case, just look at, this is the natural sampling. Watch what I am drawing here. Over above this, I am drawing the natural sampling pulses. Okay, this is what the shape of the rectangular pulses were in the previous case, that is in the natural sampling method. Now in this case, in the flat top sampled signal, just look at the top of the pulses. It actually takes the sample at a particular time instant. Let me say at this particular instant of time, I have taken the sample of the analog signal. Okay, I'm measuring the amplitude of the message signal. Okay, now I take a sample over here, and the same amplitude is stretched over a certain time interval. Let me say some t seconds. Okay, some t seconds. So, and the same amplitude level is maintained. So the top of the sampled signal remains flat. Okay, and I take a one more sample over at this time instant. Okay, and I take a sample over here, and the top is maintained flat over the time interval of t seconds, certain time interval, the pulse width, what we say. Okay, then again I take a sample over here and I maintain a flat top for a certain time interval. Then again it goes to 0. You take the sample at that instant of time and again goes flat. Okay, so this method of sampling is actually called as flat top samples. Fine. Now, one second. Yeah. So we can achieve this flat top samples, or we can get this flat top samples or a sampled version, the PAM signal, by using what is called as sample and hold circuit. Okay, so this circuit is actually called as sample and hold circuit, where we are going to take the sample of the given analog signal by using simple switch. The switch is closed at a regular interval, that is time t equal to ts seconds. For every ts seconds, the time is switch is closed. The sample of the signal is taken, and that sample will be held in the capacitor, because we know capacitor actually charges and discharges, and it holds the charge for a certain time interval, right? So whatever the time interval we have to hold is t seconds. Okay, so we close the switch, take the sample, that signal will go to the capacitor will hold that sample. So this circuit is actually called as sample and hold circuit. That means we take the sample of the analog signal and we hold we store the value of the sampled value in the capacitor. So this method is actually called as flat top samples. Now, so basically there are as I told in the previous case in the block diagram, where basically we are actually involved with the two operations. We are going to have two functions which we have to implement, and that is you have to take the instantaneous sample of the message signal for every ts seconds, as I told earlier, right, according to your sampling frequency. Then you have to lengthen the duration of each sample obtained at a constant value of t. That means for a time interval of t seconds, we have to stretch or lengthen the amplitude, or we have to maintain or hold the amplitude of the signal, the sampled value, for a time constant of t seconds. Why it is required? Why it is required? Because we have to avoid an excess of channel bandwidth. Okay, otherwise, if I go with the delta functions and all, we need actually infinite bandwidth. Okay, so as you know, the bandwidth is actually inversely proportional to the pulse duration. Fine. So to reduce the bandwidth, we have to maintain for certain time interval, small time interval, so that you can get a flat top samples. Now, let us discuss what is the mathematical equation in the time domain for a flat top sampled signal, and how we can achieve this flat top sample signal, or how this derivation is actually basically done, which I will explain now, starting from this particular slide. Okay, now you already know what is instantaneous sampling is, right? We have an analog signal. We take instantaneous samples over here, which repeats for every ts seconds, or delta functions, set of delta functions. Whenever we multiply the analog signal with set of delta functions, we will get a instantaneous or ideal sampled signal like this. Okay. Now, this is nothing but this is g delta of t. Okay, my first signal is g of t. The second signal is delta of t, set of delta functions. The third one is the multiplication of this and this, which is nothing but it is g delta of t. That is the sampled version of an ideal sampled signal. Now, we use set of rectangular pulses, which I call it as h of t over here. Okay, and when I convolve g delta of t with a set of rectangular pulses, we will get flat top sampled signal. Okay, the convolution operation between this one, the g delta of t, with a set of rectangular pulses, which is h of t, which gives you a flat top sample signal here. Now, coming to the derivation part. So, as I told earlier, s of t is nothing but this is the s of t signal. Okay, a flat top sample signal, which is nothing but convolution of this and this. Now, what is S of t? S of t is nothing but it is in the form of integration. If I consider convolution integral function, this equation can be written as integral g delta of t h of t minus tau dt or d tau. Now, substituting that g delta of t for instantaneous sampled signal, okay, in this particular equation, we will get this is nothing but this particular term is nothing but, or if I highlight this, this is nothing but instantaneous sampled signal. Okay, this is the time domain representation of the instantaneous sample signal, or this particular signal we can represent in the time domain as something like this. So I substituted that g delta of t in this particular equation. Now, yeah, if I interchange the order of summation and integration over here, if I take this outside, completely outside, okay, integration of this one and this one, if I take separately, just look at this. This is the equation I'll get. Summation g of nts is taken out and integration of these two functions. Okay, now by applying the shifting property to this particular term, that is integration of delta of t minus nts h of t minus tau d tau. Okay, by using the shifting property of the delta functions, if I consider what that shifting property says, shifting property says in general it is integral of certain function x of t multiplied by delta functions which repeats for every t naught seconds. It is nothing but x of t naught. That's all. Okay. Now, if I apply the same rule to my previous equation, okay, if I apply to the previous equation, this equation, if I apply over here, this can be written as h of t minus nts. Okay, substituting this in the previous equation, okay, we can write it as s of t is nothing but it is summation g of nts and integration. This integration is completely replaced by what? H of t minus nts. Fine. So this is the equation in the time domain for a flat top sampled signal. Now, let us go to the frequency domain representation of the flat top sample signal. Now, as you know, convolution between actually, just look at this. The convolution between the instantaneous sampled signal with a series of rectangular functions, okay, rectangular pulses, will give you the flat top sampled signal. If I take a Fourier transform to this particular equation, a convolution in the time domain is nothing but the multiplication in the frequency domain. Just look at this. S of f is equal to what? G delta of f multiplied by h of f. Now, if I substitute g delta of f for instantaneous sampled signal, which is given by fa, summation n goes from minus to the plus infinity, g of f minus nfs. If I substitute over here, what I'll get? I will get this particular equation. So the equation in the frequency domain for s of f, a flat top sampled version, is fs summation g of f minus nfs multiplied by h of f. That's all. Now, see, when we go to a flat top sampled version, or if I consider a rectangular pulses as sampling signals instead of instantaneous pulses, okay, we face a problem called as aperture effect. This effect we will get in the practical sampling methods. We will not get in the ideal sampling method where we use delta functions, something like this. The delta functions we use, something like this. The delta functions, series of delta functions, where the width of the pulses are 0. Okay, in the rectangular pulse, just look at this. We have a certain width of interval t seconds. Okay, so in such cases, we actually face a problem called as a aperture effect. What is this aperture effect that we will understand? Just look at this. This is the h of t which I have taken. If I take a Fourier transform to this particular equation, we actually get what is called a sinc function. Okay, h of f is equal to a rectangular pulse in the frequency domain is given by tau, sinc of f tau exponential minus j pi f tau. If I plot it, I will get something like this: a sinc function, set of sinc functions, the magnitude of the the frequency response of set of rectangular pulses. Now just look at this. As the frequency increases, this is the frequency axis, right? The x-axis frequency axis. As the frequency increases, we actually face, for a particular signal, we actually face a problem of, see this, the magnitude is going down. At low frequency, we don't face any problem, but at high frequency, we actually face a problem, which is nothing but a magnitude of the spectrum actually goes down. So the problem with this is we actually face a problem with the noise. Okay, so aperture effect is nothing but it is the change or distortion what happens at the higher frequencies. Okay, so this figure actually shows magnitude of the Fourier transform of h of f versus the frequency, as I told. Now, as I go to the frequency of flat top samples, we actually going to face what is called as a distortion, isn't it? Amplitude distortion at the higher frequency when I reconstruct it in the receiver. Fine, because of this nature of the spectrum for rectangular pulses. Now, how to mitigate this problem or how to avoid this problem, that we have to understand. Okay, so this high frequency roll off, okay, act like a high pass filter and attenuates the upper portion of the message spectrum. That means at the higher frequency we actually get a amplitude distortion. Now for this, okay, as I told, this is aperture effect. For avoiding this, we have to use what is called as a equalizer. Okay, in the receiver, after passing through a reconstruction filter, basically, which is a low pass filter, right? The reconstruction filter is nothing but a low pass filter. So after reconstruction of the message signal, we have to pass through a equalizer, an amplitude equalizer, which actually increases the amplitude for high frequency signals. Okay. Now, what should be the response of this particular equalizer? That is very important. Okay. The equalizer, which is connected in along with this reconstruction filter, okay, actually increases the amplitude of the high frequency signal. And to avoid that aperture effect, we have to use this equalizer. Now, the response of this particular filter, the low pass filter, which is given by this, which is because it is a reconstruction filter, a low pass filter in the frequency domain, it is T tau sinc of f tau exponential minus j f tau, because the filter is having a response which is given by something like this. A high frequency filter, sorry, low pass filter, basically it is a low pass filter, and the response of that can be written as in the form of sinc function, something like this. Now, what should be the response of a equalizer? The response of the equalizer, just look at this. The H equalizer of f is actually equal to what? K, which is a constant, exponential minus j2 pi f td divided by H of f. That is, this particular constant divided by the response of the filter H of f. That should be the response of your equalizer. Okay, where this K is a constant and TD is nothing but it is the time delay, okay, which is offered by the equalizer or offered by the filter. Actually, basically it is offered by the filter to now pass the signal from input to the output. The time taken by the filter to pass the signal from input to the output is nothing but it is a delay or a delay time, and this delay time should be equal to always tau by 2. It should be half of the tau. Okay, now I substitute that over here. As I told you here, TD is nothing but it is the delay introduced by the low pass filter, which should be equal to tau by 2. Okay, now substituting all this in my equation, that is H of f, I will substitute in the denominator. TD equal to tau by 2, I substitute in the numerator. Okay, so after substituting and cancelling the required things over there, this and this term will be cancelled anyway. Okay, this and this term will be cancelled. We left with K in the numerator and tau sinc f tau. So this should be the response of the equalizer to avoid the aperture effect. Okay, now, yeah, this is what I said. Yes, so to conclude this video, what I have explained in this video is a type of PAM that is called flat top sampling. Okay, and the problem what we face actually in the flat top sampling, that is called aperture effect, and how to avoid that particular problem by using a amplitude equalizers. Okay, thank you for watching this video.